Yes, yes.
Cool, thank you. So this is Undermaps. This is probably one of the larger utility models again in the world. What we're showing here is the utility records only. So we take all existing records from all utilities, be that from GIS data, from CAD, computer-aided BIM records, anything that is existing. We have automated tools to georeference those PDF drawings quickly. We have a service to do that, or people can do that themselves, and we can then extract that. We fully automate the vectorized imagery, the vectorized data off the back of that georeferencing tool. So here what you'll start to see is we've got a broken network link on the stormwater. We have all of the metadata that is provided by the individual asset owners, and this particular asset owner is, where is it here? It's owned by Auckland Council. This is the owner, but this is the muddy schema in terms of the data. Now, we don't generally have any depth information on the utilities. We just have a lot of GIS 2D data that's sitting in there. But the really important step is to bring all that information into one space. Next step we do is a system called Underdots. So we have a proprietary processing technology to take multi-channel ground penetrating radar, which can be driven along at road speed, so 20 or 30 kilometers an hour, goes down 6 meters. And instead of doing all the very laborious interpretation, we now process that into underground point clouds. So you don't need to be a specialist to understand that there is possibly a utility or an anomaly there, and we can start to see these underground point clouds. The different colors represent intensity, are probably not very important, but what is important is that if we were planning to do a project for this massive big light rail project, if they were planning on using this corridor here with just the existing records, we're actually identifying there is a significant anomaly or a number of unknown utilities in the ground. This also helps us verify where other utilities are. So we're seeing some evidence of this point cloud, which is probably these particular power assets because they follow the same vector and depth. Now, this is just a really good insight for us to understand where we have subsurface risk. We do this, we've got a big project in the US at the moment where they're driving it, we process the information overnight. The next day, the contractors are out digging holes on these particular points, and it increases the rate at which we're getting insight and decreases the cost. What also happens from there, I'll turn off underdots, we turn on detections. So detections follows that usual process. This can be from above ground, aerial imagery, from satellite, from drone, from fixed wing, also from 360 imagery. And you'll see this particular chamber here has been classified and identified from above ground capture. It's been qualified as quality level A, which is the highest because we have a lot of accuracy around that, but also where it was captured and what it means. So this has been identified to say, well, we think this is the stormwater node. It is not actually where the existing records say that it is. These purple lines here you can see are the ground loops of the traffic management systems, plus a whole lot of unknown utilities. But really, when we get into how we analyze this is what we call the unified utility model. Now, the unified utility model is a single representation of all underground utilities based on evidence, and this is fully in 3D. So what we can identify is not only where all the utilities are, we can identify unknowns through normal utility surveying processes. We follow a rigorous process in how we identify what it's been detected to quality level B1. We also 3D model the tolerance of error and the depth associated with that particular utility. So you can see here, there's the tolerance of error that's 3D modeled around that particular unknown utility, and we have depth pins associated to each of those points. In addition, we can also look at this because we have some areas have been detected and some areas have not. Every time we go out and say, for example, we have I'll turn on detections again, it'll get a bit messy, but we'll look at potholes, or forgive me if I don't know the word, a trial trench, or identifying where we have particular holes. We can go through and start to capture where we have more accurate imagery or information. So actually, if I turn that on, if we turn on quality level here, we can see this particular point of this line here is quality level A. We know it's 100 millimeters, and we know the accuracy associated with that, and how it's been identified. It's been identified visually. But at a macro level across not only networks, and we can filter by networks, whether we filter by asset owner, asset type, we can have a look across the entire network as to where we have accuracy and where we do not. So at a macro level across cities, across networks, we can look at our data debt and start to look at more risk-based analysis of how we look at the utility data. A few other areas that I think would be of note is how we do as-builts. So as-builts forever should now only be done using photogrammetry, and we support that. So for example, I go to say this here. If we've got existing records like base scans in the area, we can start to use photogrammetry, and this was captured in about 2 minutes using an iPhone, which means you don't need to go and buy expensive equipment. We've already got the equipment in our pockets because it's a 100 megapixel smartphone and it has all that data there. So now we're reconciling not only the new utilities, so these are 2 new laterals for a big new bulk water main that's come in. We then model these out using game engines like Unreal Engine. We have software that automatically models these, and then we can show the true connection into the bulk water main. Plus we get to update the data. So the mapped utility data said that water main was there, and we can see a slight increase now because we've been able to visually identify this. Another one methodology that we use when we're looking at mass rapid capture of cities or countries is if we have accurate positions of the lid, and let's say, for example, this chamber here, this is a chamber of a communications network. We model this using game engines as well to create the accurate IFC model. But if we look inside the evidence, we now get to see full 360 imagery. Now this was captured with the GoPro 360, or also iPhones as well. And the level of detail we can get across these thousands and thousands of chambers quite quickly using the existing field crews and teams is really, really quick. And understanding where these utilities are and feeding that back in is pretty key. I've gone very, very fast. I'd like to rather have a presentation from me. I'd rather have conversations around key areas that people would like to talk to. So I'll just stop there and then we can take any questions.
Sam, can you talk a little bit about the use of the phone in that what you show looks like an underground facility? Was that open up and then the phone used to capture the images and the video?
Yes, yeah. So this one here, we're constantly testing different sensors. Really, I care around what the cell phone, because everyone has a smartphone in their pocket. So this is just put on a pole and then pushed down the hole. You can actually see the team from the top. But these 360 imagery can be captured on a very cheap GoPro 360 or on an iPhone. Now we build all that evidence back into that particular asset node, and you can see all that evidence associated with that. Example, we could look at this sewer system. If we look at this particular chamber, it might have evidence on it. That one doesn't. But the customer goes through and identifies areas where they want to look at this. Now, if we look at the photogrammetry, for example, and we can show you thousands and thousands of photogrammetric examples like this. Yeah, this was just used with an iPhone using, we've got a sister photogrammetry company. So this is captured without any GNSS data. So when the scan is captured and processed, we do the processing. The relative accuracy, how accurate is this relative to itself, is millimeter accurate. It's incredibly accurate. But its its absolute accuracy, where is it in space, is very, very poor. This, I think, initial scan ended up over here because of the lack of ability to see enough satellites. But because we've already got base scans and we know where different areas are, there's methodologies where we can go through and manually reconcile that or automate that in the future, so that when people are doing as-builts of new utilities that are going in the ground, we can go through and bring this in. And that way, at the end of that day, you are seeing what has been installed or other unknown utilities have been found. Does that cover off that question?
Yes. เปิดให้มีคำถามหน่อยวันดีถามภาษาไทยก็ได้เดี๋ยวช่วยแปลให้
จากการพรีเซนต์เมื่อสักครู่นี้ทางเจ้าหน้าที่มีคำถามใดๆเพิ่มเติมไหมคะสามารถถามได้เลยตอนนี้นะคะถามเป็นภาษาไทยก็ได้ค่ะ
What's also helpful in terms of rapidly mapping the underground is using mobile LiDAR. So this is a GeoSLAM. And we can quite quickly create full 3D networks just off we're about how do we capture the underground very, very fast. Now, all of this we would supply to local people to undertake this work, but this is the level of granularity and detail that we can do to roll out mass data capture. I understand on the call we're looking at water utilities and also electrical utilities, so I'm more than happy to take specific questions on how we look at those individual utilities as well.
Could you talk also, Sam, about the water leak detection?
Yeah, so that's good. What can I show you? Water leak detection is becoming more and more prevalent. There's different ways that we've been able to attack that for different cities. We work closely with, I speak at Hong Kong Poly University, who have probably got the best water leak training facility there, and I speak there every December. As part of that, that's one methodology for looking at acoustics effectively is a main methodology for how we look at detecting underground water leaks. At a large level, we would look at synthetic aperture radar. So using the L-band from satellites, we can look at moisture presence. So where we've rolled that out across large areas, we've been able to run synthetic aperture radar, look at moisture, correlate that with the location of the water utilities, and then also use on-the-ground, ground-penetrating radar to validate those to a smaller area, and then target that using acoustics. So there's a pretty high-level, broad understanding as to how we look at how we look at water leak risk, and then we go all the way down to make that as cost-effective as possible.
Sam, the Waterworks already deployed the L-band radar data. So can you take it from there where you could bring the system in to further investigate or help to pinpoint the leak?
Yes. Yeah. Well, I mean, if you look at I don't have any heat. Do I have any heat maps on here at the moment? I can't show you. We're working on a big project in the US at the moment, which I'm not allowed to show. But once I can show some examples of how that's worked actually. So taking that L-band, we can look at those heat maps. We're doing that mainly for pavement as well. So the 3D modeling of pavement, so road pavement, they really are concerned around the presence of moisture and utilities, moisture with relation to the utilities. So we're using that L-band to then classify through auto classification moisture within a road area within relation to the utility data that we have. For example, we would be looking at, say, key nodes where we have a water junction here, or where there might have been historical construction. Say, for example, there might have been a new utility that's come across here. If we know where the new utility has been, there's high likelihood and risk that that was where a particular cut may have been. So that's how the L-band's used at a higher level.
โอเควันนี้คำถามมีไหม
เจ้าหน้าที่จากการไฟฟ้านครหลวงและการประปานครหลวงมีคำถามใดๆเพิ่มเติมไหมคะหรือว่าต้องการสอบถามตรงส่วนไหนสามารถสอบถามได้เลยนะคะเป็นภาษาไทยได้ค่ะ หรือว่าสามารถที่จะส่งข้อความมาทางแชทบ็อกซ์ได้นะคะ
พี่ลิมมีคำถามอะไรไหม
Pretty sure these ones were some L-band detections in terms of the water leaks on this particular project, and you can start to see where some of these more invasive investigations have undertaken. And again, this is pretty good data from a cell phone. Without any survey, we're able to ascertain the actual locations of the utilities, also inside the chambers as well.
Okay. Sam, can you talk a little bit about the equipment and the technology used with AI, with the Snake and other devices in
Oh,
the field?
yes. Yeah. I can show you on a different project. Let me just go back up. So in terms of rapidly modeling underground data, it is not true that we have to go out and do mass rapid capture of all the utilities. We can look at what existing information is in place. So as I said before, we take existing records, PDFs, but one of the other ones is CCTV inspection data. So we can take decades, years and years and years and terabytes worth of CCTV footage, and we can use that to then create 3D models of, it's the wrong one, 3D models of the underground based on the CCTV. So if it looks at the image analysis, it'll say it entered this chamber, it's gone to that chamber. It takes imagery analysis off the back of the chainage of the CCTV data, and it creates a 3D line string off the back of the imagery. So that gives us more confidence now, which is great because it's cost effective. We're using the existing data set, and that's helping us move towards the actual accurate representation of the 3D data underground. The other one was with respect to how we look at a lot of this modeling. So if we say across this project here is where we've used AI and we look at quality level, anything that is red means it is quality level D, which means that we only have the existing GIS information or CAD information. And you can see here there's network links and breaks in there. But by using logic and a lot of the evidence-based approach, we can start to correct this. And this identifies where we've made those corrections off the back of evidence and AI. Now, that means we can look at very, very targeted areas we want to improve that. For example, an inspector might go and open up this particular chamber, and that then really improves this whole part of the network. The same applies for water, the same applies for power as well. We're working with big power utilities around how we get this information in. But using AI is helping us rapidly 3D model these particular utilities based off evidence, which means there's not a lot of processing that needs to happen.
Can you show us some of the images that were used and the equipment that was used?
Yep. Let me just bring up, I'll stop sharing, I'll quickly bring up a slide. While I bring that up, are there any more questions?
ท่านใดมีคำถามเพิ่มเติมสามารถสอบถามได้เลยนะคะ
ขออนุญาตนะครับผมสมฤทธิ์นะครับไม่ทราบว่าจะมีผู้แทนของการประปานครหลวงหรือการไฟฟ้านครหลวงจะพูดอะไรสักหน่อยดีไหมครับหรือมีคำถามหรืออะไรที่จะนำเสนอไหมครับคุณพัฒนาการคุณธนากรหรือคุณธนบดีนะครับเชิญเลยครับผู้แทนก็ได้นะครับ
So, do you want me to continue?
Yes.
Cool. So this is a single channel ground penetrating radar. This is a 450 megahertz antenna. This will go down maybe 2 meters, but it has one signal. It has a transmitter and a receiver. So that looks for anything in the ground. This here is electromagnetics. So this is looking for the electromagnetic field. For those from the power sector will know what these are. This is what's used to trace anything that is ferrous in terms of copper or steel. So yeah, and you can induce using different methods. For example, in this, I'll go through some maybe different pieces of equipment. Let me find out. So in terms of this, it's locate and mark out where you're putting paint on the ground pre-construction, that uses not only a single channel ground penetrating radar, but electromagnetics. So this is an electromagnetic unit, this is the receiver, and this is a transmitter. This is a multi-channel transmitter. So this has 16 channels, everything from 8 kilohertz to 200 kilohertz, which is optimized based on the different conductor sizes. So this is used in terms of locating power, gas that has tracer wire, water, HDPE water or PE water that has tracer wires on them, cast iron, and ground penetrating radar as a supportive piece of equipment as well. Here's an example of a very small CCTV camera that's pushed down to look at different imagery inside there. It's just a camera on a large snake. But then you would use electromagnetics to go through and trace that particular line, and there's lots of automated stuff to do that as well. We are working with a couple of partners now that have drones, and the drones can go down the stormwater and the sewer network lines, and you can trace that there. But it's pretty new technology. It's not well managed at this point yet.
Could you show how AI is used in putting together the images for the height of the pipe?
In terms of the 3D modeling of all the pipes?
Yes.
I can't show you the AI part of it. What I've shown you is probably the output of what that's given us. Just trying to think where there's some good examples. We can go right into the different details, but we've got quite a significant workflow through the background that's pretty proprietary to what we're developing.
Can you show what's captured from the snake and how it was turned into the data for the model?
Yes. Yeah. I know they use it on here, so let's have a look. Let me just find some. I can show you how the reconciliation happens in terms of that. So we will find a stormwater line. Here we go here. So this is just the output from that investigation. It's a 3D line string, so it shows how it's been collected. The imagery will be inside. We haven't brought any of the imagery through, but the imagery can be brought into there very easily. But this is the output. It's getting a shapefile or a CAD file, a line, a KMZ line that goes through. Now that only gives us effectively like a cookie crumb, like a line string of that stormwater, but it'll have the metadata around who captured and when. So that gives us that confidence, and that's been classified in terms of the B level. Now when we go through and we apply the UUM, so the Unified Utility Model, that has followed that. Now that's been detected through a number of different methods, so you can see there's a slight variation in that, and we'll see why that is. We look at the Unified Utility Model, that'll say that it doesn't have enough evidence there. So the actual water authority, and you can see how accurate that is. There's only a small discrepancy between elevation here. Oh, too far. You can see this small discrepancy between this particular stormwater line off the back of the CCTV data and what has been detected, because it's also had ground penetrating radar. So you see there, partial detection by UWB, which is ultra wideband radar, and this is the output. So now we've got this accurate 3D line. So if I turn off the detections, we've got the 3D pipe associated with two different pieces of evidence supplied from Auckland Council, which is their existing CCTV footage, and that we have the tolerance of error, which we can turn on associated with that particular detection or the two different detections. But what's really important is we're now can go, if they've got their GIS system, we can now feed that back into their GIS system as to an accurate location of that particular utility. And once this loads, now if we reconcile that against their existing records, so this is where they said their existing records were, which is here. And now we've had through their existing, not only through their CCTV footage, we have evidence here. They now have confidence to move their records to this particular point based on evidence.
Do you have any actual footage to show?
No, not of the, I mean, it's pretty boring CCTV footage. I mean, I can show you one still of what that looks like.
Okay.
Let me just go to
ผมขออธิบายนิดนะคือว่าข้อมูลตรงนี้มาจากการที่เขาใช้ไอ้ตัวกล้องที่ติดกับเขาเรียกอะไรงูหรือลวดอะไรที่ใส่เข้าไปแล้วจากตรงนี้ก็ใช้ AI ในการที่ process ตำแหน่งและความกว้างความสูงของตัวนะครับ
Well, this goes into some of the rapid void, the water leak modelling. So we've looked at anomalies across an entire city. We've classified these. This is a mixture between ground penetrating radar and synthetic aperture radar. We can take this. We looked at the high areas. Here's an example of a possible void in the water lateral, which we thought was a leak. Here is another example. Here you can see on the right, this is ground penetrating radar data. So this is an elevation view. So this shows the trace distance and the depth. And you can see an anomaly in the radar data. And also from a metric view, you can see there's an anomaly there in the radar data. This was identified on this particular water line. On CCTV investigation, and this is pretty bad footage, but this is a 450mm earthenware line. And you can see the water leak coming through the stormwater line. Now the water leak was creating a void inside the ground because it was pulling all the fines of the soils out, and that then ended up causing this, which meant that the city had to go through and replace this 450mm earthenware line. But by having all the utility data, we're able to not only see where all the utilities were to execute the construction safer, but also that these three lanes here had reinforced concrete. And by understanding that we had reinforced concrete in these lanes, we could see where we were going to have variations in the project. So preceding the replacement of the line, they were able to go through and cut out the reinforced concrete, backfill with reinforcing, and then go through that way. So it was a huge opportunity, a huge win there. But in terms of CCTV footage, this is effectively what you get. It needs to be anything above probably a 100mm line, but it does cost a bit. But there should be a lot of existing information there if people are working through normal asset management and repair programs. Does that help?
Can you talk a little bit about the process by which you can take the images and tell how the pipe actually turns, where it turns, deriving that data from AI so that you could use that as part of the input into making the network more complete?
Yeah, so I can't show you how that works, but what it does is it takes every frame and it looks at a vector off the back of which way the camera's heading. Inside some of the equipment as well, it has inclometers, so an inclometer, so it knows where it's sitting. So effectively with a gyro, it knows what vector it is pointing. As that vector changes, it will aggregate all of those, and based on the imagery, you can't see it in this one here, but typically they will have a chainage, like a number on the bottom where how far it is from a particular chamber, and it goes through and uses that to correlate into the 3D line strings.
ผมขออนุญาตแปลตรงนั้นนะคือที่เขาใช้นี่ก็คือตัวกล้องแล้วก็ในตัวกล้องจะมีเรียกว่า incline meter ก็คือจะบอกได้ว่าทิศทางของกล้องแล้วก็มันจะเล็งขึ้นหรือลงตรงไหนจากตรงนั้นเนี่ยในการที่เขาใช้ AI มา process เนี่ยมันก็จะสามารถที่บอกได้ว่าท่อที่เขาใส่ไอ้ตัวกล้องนี้เข้าไปเนี่ยมันไปทางไหนวิ่งไปถึงตรงไหนยาวเท่าไหร่นะหมายว่าตัว GPR ก็เป็นวิธีหนึ่งแต่อันนี้คือวิธีที่ confirm และเห็นตัวภาพด้วยคือใส่กล้องลงไปซึ่งตัวกล้องเนี่ยจะมีข้อมูลจากไอ้ตัวที่สามารถที่จะวัดทิศทางของกล้องและตัว angle ของมุมของไอ้ตัวภาพเองเอาตรงนั้นมาประกอบที่เป็นการสร้างข้อมูลของท่อจากข้างในครับถ้ามีคำถามถามได้เลยนะครับภาษาไทยก็ได้ช่วยแปลให้เป็นวิธีใหม่ครับในการที่จะหาไอ้ข้อมูลจากข้างในท่อโดยใส่ไอ้ตัว CCTV เข้าไป เอาละครับมีค